This video is on atomic emission spectra and connecting the idea of energy levels and emission and absorption back to what we know about the electron. Okay, so back when scientists were attempting to learn more about atomic structure and specifically about electrons, they started studying light. Okay, and the first thing they studied was sunlight. And they took a prism, which most of us have probably worked with a prism at some point. And then they took a prism, or even something that's called a spectroscope, which is a device that separates white light into the colors of the rainbow. And they took this prism and allowed it to separate the light coming from the sun. And it gave a rainbow. Okay, the full Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And it gave those bands of light within the visible wavelength ranges of 400 nanometers, or 700 down to 400. Okay, and so they were able to view all the colors of the rainbow coming from the sun. So then in an attempt to learn more about atomic structure, instead of looking at sunlight, they started looking at the light given off from different gases. And they started with the simplest gas, or the simplest atom that there is, which is hydrogen. Okay, and so they put hydrogen gas into a glass cylinder, I guess, and connected that to a voltage source, like a battery. And they turned the battery on, okay, and they saw the hydrogen, and it glowed kind of a pink color. And so they thought, oh, that's kind of cool. And then said, well, I wonder what will happen when we use the same idea of a prism to separate that pink light. Okay, so before I do that, I'm going to kind of summarize. So they put hydrogen gas into a glass container. Oops. And allowed electricity to pass through. And then they separated that light with a prism, just like they did with the sunlight. Okay, now, because when they studied the sunlight, they saw the rainbow, they thought they were going to see the same thing. All right, so that was their hypothesis. They thought they would see a rainbow. However, they did not. And instead, they saw these four specific lines of light. They saw one red line. They saw a blue line. They saw an indigo line. And then a violet line. And they're actually able to identify the wavelength of these lines. And so I'm going to add that to my picture here. So the red was at 656 nanometers, the blue 486, the indigo at 434, and the violet at 410 nanometers. And they were perplexed. They said, where's the rainbow? How come we're not seeing the rainbow like we did when we looked at the sunlight? Okay, so they thought they were going to see a rainbow, and they didn't. Instead, they saw these four specific lines, and they come to be called they come to be called spectral lines. And they were puzzled. Okay, they were very puzzled. So then on a whim, they thought, well, maybe that was just hydrogen. Like, for whatever reason, maybe it was hydrogen that did this. So they instead filled that tube with neon, and then they tried argon and a bunch of different other elements, and they got similar things. Now, they didn't all resemble hydrogens with the 4 lines. Okay, some of them had more lines, and some of them maybe had a yellow or an orange line and a green where hydrogen was missing that, but they were very similar, and none of them gave the full rainbow. So they were really puzzled and really didn't know how to explain this. Okay, and so what happened was a period of time went by where the scientists attempted to explain this. Okay, and so that's what we're going to talk about now. And so the scientist who is kind of first credited with attempting to explain this perplexing discovery was a scientist by the name of Balmer, and he made a pretty bold hypothesis. Okay, and so basically he said that these electrons in the atom can move between energy levels. And when they fall down in energy levels, they emit certain wavelengths of light that have specific colors, like we saw with hydrogen. So this goes back a little bit to when we talked about emission, right? That for light to be emitted, first electrons have to be promoted from the ground state to the excited state by absorbing energy, and then they don't hang out in that excited state for very long. They fall back down to the ground state, and when they fall down, they emit energy, and that energy is what we see or sometimes don't see if it's outside of visible light. So Balmer used this idea, okay, of the spectral lines of hydrogen and kind of said this. So before we go any further, I want to talk about this. The fact that we know that energy and wavelength have an inversely proportional relationship. So when wavelength is big, energy is small. Okay, so this red light, which has the biggest wavelength, would have the smallest energy value, and the violet, who has the smallest wavelength, would have the largest energy value. And that's going to be important in our discussion in just a minute. So Balmer takes this idea and says, okay, look, the reason we're seeing these 4 different colored lines is because there are electrons that are falling from certain energy levels. They're giving off a specific energy, which corresponds to a specific wavelength, which corresponds to a specific color. And that's why we see red, blue, indigo, and violet. And so to concrete his hypothesis, Balmer does this. So this is kind of a different view of the nucleus and the energy levels. Obviously, we have the first, the second, and so on and so forth. In terms of energy levels. Notice they're not equidistant from each other. Okay, as we move farther from the nucleus, the energy levels get closer together. And that is actually true. That was able to be proven. So Balmer said, and bear with me because this is kind of strange. Balmer said that violet line, okay, that we see at 410 nanometers, has the biggest amount of energy of the 4 spectral lines. And so Balmer's proposed that there was an electron in hydrogen that was falling from level 6 to level 2. Okay, and that specific energy value, right, the energy difference here corresponded to that violet color. Okay, so then he said, well, then the indigo, which has less energy, is falling from level 5 to level 2. And that energy distance, okay, or that energy gap, is specific to the indigo color. Same thing with blue, but with even less energy, it was falling from level 4 to 2. And this energy gap corresponds to blue. And then red, the same thing. So Balmer publishes this data. They call it the Balmer series of spectral lines, and Balmer wins the Nobel Prize. Okay, so kind of interesting. So then if you're friends with Balmer, maybe you're thinking, oh, wait a minute, Balmer, what about all these other, like how come we're not falling down to level 1? Okay, so there was a second scientist, and his name was Lyman. And Lyman says, okay, Balmer, I think your idea kind of makes sense, but if these transitions can occur, how come they can't fall all the way to level 1, like this? Okay, but what Lyman proposes is that while this is happening, they're falling bigger energy gaps, right? See how the energy is bigger than it is here? And so bigger energies would give us wavelengths that are outside of what we can see. So Lyman says, look, I'm pretty sure this is happening, but it's happening at an energy that's slightly higher than visible, and that would be UV. And so Lyman says, if only I could build a machine that could, quote, quote, see in the UV, I would see these lines for hydrogen, just like we saw the colors. So Lyman does it. I'm not sure how he did it, but he built some kind of machine that was able to read in the ultraviolet. And in fact, he was able to see these lines. Now, they're not color because remember, it's outside of visible light, but he proved it. And so Lyman wins the Nobel Prize. Now, if you're the third person in this, hopefully you're saying, well, wait a minute. If they can fall to level 1 and to level 2, how come they can't fall to level 3? So there's a third scientist whose name is, I'm not really sure how you say it. I say it as like Passion. I'm not really sure. But Passion says, okay, so hold on. If they can fall bigger energy distances, how come they can't fall smaller? And that would be in the infrared. So Passion says, I'm going to do the same thing. I'm going to build a machine that can see in the infrared, and we're going to prove that these transitions are there. And sure enough, he does. And Passion also wins the Nobel Prize. So what does this mean? Okay. So what this means is that from this discovery, they were able to prove that electrons are limited in the energy values that they can emit. And that's because there's a specific energy, I was calling it an energy gap, that the electrons are falling, thus releasing a specific amount of energy which corresponds to a specific wavelength, which sometimes has a color and sometimes does not. So what's interesting about this, and this is really hard to understand, is that for hydrogen, there is no yellow. Okay, well, the reason why there's no yellow is because in hydrogen and in how hydrogen's energy levels are laid out, there is no energy gap. So you'd have to be right here somewhere. There's nowhere for the electron to start from and to fall to that would give the right energy to be yellow light. So that's why we don't see yellow for hydrogen. Same thing with green. There's no green. Okay, there's no orange because there's nowhere for that electron to be and to fall that specific energy to give you yellow or green. Now, other elements have yellow, they have green, they have orange. They might not have red, they might not have purple, and that's because the energy levels for other elements are spaced slightly differently. So in, sodium perhaps sodium has the perfectly spaced energy level somewhere where that energy gap corresponds to yellow. And then thus, maybe there's a yellow spectral line for sodium. Okay, every element has a different emission spectra. It's actually kind of like a fingerprint, like how people have different fingerprints. Every element has a different emission spectra. And that's because every element has different spacings between their energy levels, which then correspond to different energies, which correspond to different colors. Okay, so this is a very hard topic. It's a very hard thing to understand. But one thing I want you to know is that this came first. So see, this whole chapter is taught in reverse because scientists didn't learn about orbitals and electron configurations and all of that until they first saw this. See, it was this that gave the groundbreaking discovery for energy levels and for these transitions between the energy levels and for emission and for absorption. It was this that was understood first. And then that laid the foundation for the discussion of energy levels and the discussion of orbitals and for Schrodinger to come and solve the math and to prove that there was an S and a P and a D and an F and all that stuff. So that the fascinating thing about this is that I taught it to you in the reverse of how it was learned by scientists. But see, it has to be done that way because I can't teach you this first and expect you to even try to understand why I'm teaching you this first. It has to be taught last. So, kind of tough. It's okay if you think, man, I'm not really sure that I follow that. Okay, it's okay because it's a hard topic. There's only one other thing I want to say or try to explain, and that is, why was hydrogen pink? And this is actually kind of cool. It's pink because, see the 4 spectral lines of red, blue, indigo, and violet. If you were to mix them all together, it would give you pink. And so that's why we see pink until we separate it. And then we see the 4 spectral lines for hydrogen.